What is dark energy?
Dark energy, it emerged as so-called Einstein's cosmological constant. And back in 1917 or so, the observations were such that there was no indication, that there was clearly external galaxies. And so it seemed like the stars and structure, they were just buzzing around us. So that on average, it was an equilibrium situation. And so, yet, when you take the laws of gravity, Einstein's theory, curiously enough, it would either contract or expand automatically. The contraction is called gravitational instability, and it's the way we understand how structure formed in the universe. It's the gravitational instability theory of the formation of structure. And so he said, well, maybe the data is going to enforce me, so I'm going to put in a term which the theory allowed, and it's called the cosmological constant. And then about a decade later or so, somebody proved that theory is unstable as well. And Hubble discovered the expansion of the universe by looking at galaxies nearby and how they were moving away. And Einstein, this famous statement of Einstein's that it was the biggest blunder. He never apparently actually said that, and it wasn't a blunder. It's at sort of the heart of much of our thinking, because one way of thinking about it is that it's the energy density of the vacuum, and I'm going back to the word vacuum. So when I write it, I often use rho as density. Many people use rho for density, sub vac, as if that's an obvious thing, vacuum energy, except that, as I said earlier in this brief thought flow, is that the vacuum is fundamentally deformed. It's deformed by the expansion of the universe. It's deformed by structures in the universe. So vacuum is not actually this pristine thing that people think about anyway. The bottom line is that was the original Lambda, and it was embraced by, well, I won't go into the full history of this, but it would rise up and go down and rise up and go down in terms of its stock, if you like, about whether people were interested in it. It kind of got resurrected for a few reasons around the mid-'80s. And that's when I thought it was, a great idea. Why? Because as well as matter and radiation, the universe can have curvature. I mean, in fact, it's always got curvature on small scales. That's what causes the matter to concentrate. Anyway, the basic point is that there was this first indication for me that you needed something akin to Lambda. The reason going back to the thread of thought there, curving the universe on average on large scales, and yet having small fluctuations on smaller scales, and we had evidence for that. Anyway, the basic point is you have to have this large-scale curvature if you're going to have what is called an open or closed universe, whether it's curved up like a sphere or curved down like a saddle. That was, what people mostly thought about. Whereas the vacuum energy density is something that's constant and scale independent, or at least that's the view. So then the other dilemma occurred, well, how can it be as small as it would need to be to make a universe like ours? And that continues to be a huge mystery, because if you count the amount of energy density that you think is in the vacuum, it would depend upon the Planck energy scale. In fact, it would go like the fourth power, which is a huge, huge number. like nothing that we have ever seen. Except the key element here is that you don't apparently get to observe that. You only get to observe differences or changes. And so maybe it can all be well understood that way. But anyway, so I liked Lambda. I liked it as a extension beyond just dark matter and baryons, which are the stuff that we're made of. And so it became part of my kind of standard thing. And then we were dealing with two kinds of data, cosmic microwave background as it was emerging, fluctuations that emerged from the universe around 380,000 years after the so-called Big Bang. And that's like 13.8 billion years ago. So that was giving us valuable information. It's since filled in brilliantly, but, as it emerged, it was giving us an indication. But we had to add large-scale structure to that, the spatial inhomogeneity on large scales of the universe, in order to say it looks like Lambda's pretty good. And we did. And then, so that was microwave background and large-scale structure observations. Then another set of groups, they were looking at supernova, and they were developing something, curiously enough, it's called the Hubble diagram, where it's Hubble parameter as a function of time. And if you have an ordinary universe without any lambda, it would have a certain shape. And with lambda, it has a different shape. And so after some stops and starts, it emerged that looked like it was also indicating accelerated expansion. And that's the one that sort of became the popular way of understanding of how this emerged. But the microwave background and large-scale structure were right there as the underpinning of this whole story. And then there's another experiment that I was involved in. It's called Boomerang. It was a microwave background experiment called Boomerang because you launch from the Antarctica, and the prevailing winds at the top of the atmosphere cause the balloon to go around and around and around, and so you get lots of data. And it was really the thing that sold the vast community, in particular the particle theorists, on that you have to take this extremely seriously. It's like that's clearly the answer. Then the issue is, what is the nature of this so-called dark energy? I mean, what does it mean to say an energy is dark? For that matter, this is a bit of a joke. For that matter, why do we call it dark matter? And why, since matter and energy are intimately related, why do we have this stupid label? But we do that in this subject. There are stupid labels all over the place. Some actually quite clever, but, up, down, strange charm is particle theory, right? So, there's a little whimsy that does occur, but dark energy really doesn't convey the information. It's actually potential energy density that at the moment we observe only through its impact on the expansion of the universe and not in any direct experimental way. The hope is that we will be able to, and so, billions of dollars actually have been put into experiments that give huge amounts of astronomical information, but one of their primary raison d'etre was to learn more about the dark energy, which you cannot learn from observations on the Earth in the lab. It is really something writ large in the ultra-large scale dynamics of the universe. Anyway, it emerged as being an ingredient, and as time went on, it got the observational evidence got stronger and stronger and stronger that was it. And so there are two aspects to this. One is it just a uniform potential energy density so that everywhere, including in this room, there would be this uniform energy density that's sitting there? You wouldn't really be feeling it, but if it could, it would try and expand you. It's just that the other forces are so strong that that doesn't happen. Anyway, so there's this kind of uniform energy density that we think is, all pervasive, but the evidence we have for it is on very large scales. So then the question is, does it change in time? And why is that interesting? It's because it says it might not just be potential energy, it might also have a kinetic component. There are two types when you learn physics in school. There's potential energy and kinetic energy. And so what is the kinetic energy amount of the dark associated with the dark energy? So this is a blazing question. And as I said, we're trying very hard to determine whether or not that's needed. At the moment, it isn't. And yet, some people say you'll never find it because it's uniform. It's got to be uniform. And I don't ascribe to that. I think that it can change. The thing that, to my mind, is the most interesting is if the dark energy actually interacts with ordinary matter and dark matter so that it can have a spatial dependence, not a sharp spatial dependence, but a spatial dependence that can allow us to determine more about it.
If you enjoyed that clip, then the full podcast is out right now. You can click around here. Enjoy. Subscribe to Theories of Everything to get notified of upcoming podcasts, as there are new full-length podcasts every week on the topics of mathematics, physics, consciousness, free will, and AI.